Hello everyone. We have already seen about spectroscopic analysis of drug metal complexes binding to DNA with different methods. In the class we have seen about the structure of DNA and nucleic acids. What is DNA? What is RNA? What are its compositions? How it is formed? What are the different forms of purines and pyrimidines? What is the type of sugars that is being used in the nucleic acids? And the complete, what is a nucleotide, what is a nucleoside? All this structural information about DNA. We have seen how different structures of DNA are there, what kind of interactions exist in DNA, and what are the different forms of DNA, that is different structures of DNA that we have seen about bDNA, aDNA, zDNA, cDNA, and ddNA, eDNA. But basically we talked about majorly about aDNA, bDNA, and zDNA. We have seen what is the structural parameters for these DNA forms kind of thing. Then we talked about the nature of binding sites present in DNA, how the ligands or the drug molecules bind to DNA. Is it an intercalative mode? What is a group binding mode? Major group binding, minor group binding, intercalation, bisintercalation, electrostatic binding. All these things we have seen. Then we went into methods of determination of drug DNA binding. We talked about the inductive methods, spectroscopic analysis, and we today will talk about the deductive methods as the physical measurements like viscosity kind of thing. We have talked about how interactions occurs and all those things. This absorption spectra of the drug DNA complexes. We have talked about all those things, how information is obtained from these. What are the different types of spectroscopic titrations that can be done, that is normal titration, reverse titration, how absorbance titrations are carried out, then how the binding isotherms is calculated, and how the equilibrium constant and binding constants and binding ratios are calculated. All these things we have gone through in our class already. This is about the reverse titration methods, absorbance, how the binding ratios. You have seen about fluorescence experiments, how fluorescence is obtained for DNA and drug DNA complexes. Then what is the normal titration in fluorescence method and reverse titration methods. Then we have seen about the salt back titration method in fluorescence titrations, and we talked about how K absorb is dependent on salt concentration, and we talked about complete methods involved in salt back titration. Then we saw about how the data is interpreted and kind of thing, what are the different binding isotherms that can be plotted. We have talked about the Scatchart plot called Sport-Hausen plot. Then we talked about binding species. We talked about the site excluded models, how the bonding occurs. Then we talked about the reasons of site exclusion. Then we talked about the distortions occur in DNA structures, and we talked about cooperativity and anti-cooperativity in DNA binding. We also talked about slightly about what we say is the dependence of K absorb on salt concentration. We'll have a slight look again onto this. Then we'll proceed forward with the other concept. So the binding of protein or small molecules which are positively charged to a nucleic acid is sensitive to the environment. Means it's sensitive to the salt concentration or the kind of ionic system it present in the solution. This is due to the reason that the nucleic acids, the DNA and RNA, are polyelectrolytic systems. They are negatively charged polyanions. So they have a large density of negative charge phosphate groups in their structure. So this makes nucleic acids to be polyanionic in nature. So because of this polyelectrolytic nature of these nucleic acids, there is a high accumulation of positively charged cations around it in a salt solution. So cations will be trying to interact with this negative charge of the nucleic acid. So a charge neutralization by the positive ions of the salt, like sodium ion, if it is sodium or potassium ion used in the salt solution, then it will interact with the negative charge of the phosphate group, neutralizing the charge. So so some of these cations, as potassium ion or sodium ion, which is bound to these phosphate groups electrostatically, are released back into the solution once a ligand which is positively charged binds to this nucleic acid. So this release of cation from the nucleic acid surface by the binding of a ligand to it creates a stability. Its stability increases because of this change, that is the cation that is released from the polyanion to the solution, that creates a positive entropy. So that enhances the binding ability of the ligand to the. So if the ligand is able to displace the positive charge from positive cation from the nucleic acid, then it is able to bind to the DNA more strongly. So this binding of ligand, positively charged ligand to the DNA and releasing of cation can be thermodynamically studied. So thermodynamic studies of ligand binding to DNA, the DNA lag interactions, are studied by two approaches. One is the calorimetric method, where the heat change is been measured and you calculate the enthalpy changes, and that has been determined. Other method is by determining the equilibrium binding method, where you would find the equilibrium constant based upon either spectroscopic or some other method. So let us consider this equation where we say that the nucleic acid or the DNA, represented as D, interacts with a ligand which is positively charged. The charge can be +1, +2, +3, or it's a N plus, interacts with the DNA to give you a ligand nucleic acid or DNA ligand complex. So the binding constant or the equilibrium constant can be represented as K absorb, which is equal to the DNA complex, DNA ligand complex by concentration of DNA and concentration of ligand. So this K absorb is called as the intrinsic binding constant. So the binding constant K absorb is binding of only one form of ligand to the DNA to give a DL complex. That is, if the ligand is binding only in a groove binding mode, or let's say the ligand binds to the DNA only in an intercalative mode, this is called as binding of ligand in one form. That is, one species of ligand binding to the DNA only in one form, that is either intercalative or groove binding, either major groove or minor. So only one form of ligand is binding to the DNA. But in case if the ligand is able to bind to DNA in multiple forms, that is, it can interact to groove binding as well as intercalative, so it shows different types of binding. So in that case, the total binding constant what you get is not you call it as an intrinsic binding constant, because each form of binding, that is intercalative binding, will have different intrinsic binding constant, and the groove binding form will have a different binding constant, so intrinsic binding. So the actual obtained binding constant for the total DNA ligand complex is called as an apparent binding constant, because every ligand form which can exist in an equilibrium, and that gives a separate intrinsic binding constant. And this intrinsic binding constant is described describe the interaction of each form of ligand with DNA. So the total binding constant what you get is called as an apparent binding constant. So if K absorb is an intrinsic binding constant, then it can be calculated through thermodynamic quantities, like you use the free energy concept, that is delta G naught is equal to minus RT ln K absorb, and delta G naught is equal to delta H naught minus T delta. So you can find, but as I said, if the type of binding is multiple form, then the binding constant which is measured is called as apparent binding constant. So if the measured binding constant is intrinsic, then the K absorb, that is K absorb value, will be independent of concentration of ligand DNA. That is, the concentration of ligand and DNA will not affect the intrinsic binding constant if only one type of ligand is one form of ligand is binding to the DNA. If the binding constant is apparent, that is multiple forms of DNA, ligand is binding to the DNA, then the K absorbed depends on the concentration of ligand as well as the DNA. So if preferential interaction of cations and anions and water and proton occurs with the DNA ligand and the DNA ligand complex, then K absorb will depend on the salt concentration, pH and temp. That is, if there are specific interactions of the cation to the DNA as well as the DNA ligand complex, then the apparent binding constant will definitely be influenced by the salt concentration, pH and temperatures. So this we have already studied. So how these salt concentrations will affect based upon the cationic natures. So the cationic effect on ligand. So how this cation affects the ligand nucleic acid equilibrium, that we'll see. That is based upon a concept called as polyelectrolytic effect. So the majority of proteins, nucleic acids as well as positive charge ligand interactions with the nucleic acids are sensitive to salt content. That is, protein interacting with nucleic acid DNA. So protein's positive charge will interact with the negative charge of DNA, or a small molecule or a metal complex which is having positive charge interacts with nucleic acid, that is DNA, and all these interactions are sensitive to salt concentration. So in a solution, so the nucleic acids are highly charged polyanions. So because phosphate groups are negatively charged, so we say that the DNA or RNA is a polyanion, means multiple negative charge present in a molecule. So these polyanions are highly charged species. So they always have a cation in their vicinity to reduce the net charge on the nucleic acid. So the fraction of counterion bond per nucleic acid phosphate is given as psi. That is, how many cations is binding to the one phosphate group electrostatically. That cation is called as counter ion, which is neutralizing the negative charge of the nucleic acid. So the counter ion what we have, the counter ion what we have, it is nothing but the cation what we are talking about. So like potassium or magnesium or sodium, whatever it is, right? Though it is interacting with the negative charge of this phosphate. So one phosphate group, how many cations it is binding to is so that fraction it is given as psi, and it is dependent only on the structural charge density along the nucleic acid. That is, this psi value depends only on the structural charge density along the nucleic acid, and the counterion valency, that is the cation is unipositive or dipositive, means +2 charge or +1 charge or +3. So based upon the valency also affects the fraction there, right? So that is, if a magnesium ion is there, calcium ion is there, two phosphate groups can interact with one metal ion there. So the fraction, the psi value will change there. And this fraction is independent of bulk salt concentration. So salt concentration doesn't affect this fraction because it is only at the vicinity of the nucleic acid what we are talking about. So for a double stranded DNA, like a B form DNA, the psi value is expected to be around 0.88, that is nearer to 1. That is, one phosphate group interacts with one cation when valency is considered to be 1. And for a single stranded nucleic acid like RNA or single stranded DNA, the psi value is considered a fraction of counter ion bonding per nucleic acid phosphate group. That is, per phosphate group around 0.7 to 0.774 is the fraction of counter ion, that is the cation binding to the phosphate group. So the lower value of psi for a single stranded nucleic acid is due to the lower charge. So in a double stranded DNA, the charge density is large because in a particular region the number of phosphate group is more, so the charge density is more. But in a linear nucleic acid, or you can say single stranded nucleic acid, the charge density is less, so that's why the fraction of counter ion bond is less for a single stranded nucleic acid than a double stranded DNA. And these are experimentally confirmed by sodium NMR studies, where if a sodium ion is used for a DNA solution by examining the salt dependence on number of oligocations interacting with duplex and single stranded nucleic acid. Oligocations are nothing but small molecules which can bind to the DNA and displace of these cations from it. So oligocation means oligo group, like two polymers, like two polypeptide, two amino acids, or two sugar groups bind together having a positive charge. They are called as oligocations. So they do bind to a double-stranded DNA or a single-stranded DNA, and they displace of these cations from it. So the association of simple cationic ligand with net charge of Z plus, that is whatever the charge is on that on the cation, with DNA in presence of excess of univalent salt, that is MX if we take, right, like sodium chloride, right, or potassium chloride. Univalent salt MX concentration is represented thermal. So in presence of salt, the ligand DNA interaction, where the ligand with a charge of Z plus interacts with Gl to give you the fraction of counter and release the charge on the oligocation or the small cation and the metal ion that is from the salt, right? So the coefficient Zi includes a contribution of direct release of cations previously bound to the nucleic acid, as well as the perturbation of electrostatic screening of the phosphate by the remaining of the bulk ions. That is this constant coefficient what you have, it's a constant kind of thing. It depends upon the cations released from the bound nucleic acid, as well as the electrostatic screening that has been removed from the phosphate group, right? So based upon Le-Chatelier's principle, the K absorb value, if you take the log of K absorb by log of concentration of metal cation, salt concentration, that is metal there, gives a constant that is minus Z psi. So the coefficient Z psi is constant for a given ligand. So if I take a ligand like ethidium bromide, it's a positive, unipositively charged cationic ligand, so that will have a specific Z psi value. Same like ruthenium complex, if you take with a plus 2 charge, it will have a different Z psi value. So like that, ligand to ligand, this constant will change because the extent by which this ligand will displace of the cation from the surface of the nucleic acid to the solution will be different. So that determines that too in presence of a particular salt. That determines the K absorb values kind of thing. So this coefficient Z psi is a constant for a given ligand and nucleic acid complex. Therefore, the log of K absorb will decrease as a linear function of monovalent salt concentration. So what it says here from here, that is the binding constant K absorb is inversely proportional to the salt concentration. As the salt concentration increases, then the binding constant for the particular ligand to the nucleic acid will decrease, and the K absorb will increase if the salt concentration is decreased. So at a lower concentrations only, the ligand will bind more effectively to the nucleic acid than the higher concentration of salt. So the preferential cationic interaction with nucleic acid results from two reasons: the cation release from interaction of phosphate charge, and because of intercalation of ligand, the charge spacing of duplex nucleic acid increases. The former effect dominates the salt dependent. That is, the cation release from the interaction of phosphate charge, that is the phosphate charge, the negative charge of the phosphate, when it the ligand is binding to this nucleic acid, this cation should balance the charge of this phosphate group, and it should able to release this cation from the salt which is binding to the nucleic acid. So this is having an entropic effect, so a positive entropy, so that if that is more great, so the binding constant will increase, but that is in case when there is a lesser salt concentration. And there's one more reason, that the charge density also slightly decreases if there is a intercalation mode of the ligand. So if the ligand binds with intercalation, the length of the nucleic acid also increases. So when that spacing between the bases increases, the charge density also decreases, so the cationic is released more easily, right? So this is a curve kind of thing, graph, where we can see the concentration of salt, that is potassium nitrate or potassium chloride, K plus ion, versus the log K absorb value for ligand with different charges, you can see. So plus 2 charge, plus 3, plus 4. So you can see these are slope values, that is nothing but the Z psi value what we talk about, right? So for as the charge increases, you can see the Z psi value is also increasing, and the slope here for the molecule with 10 charge plus 10 charge is more, but at a higher concentration, if you see, this is minus 2 log means 0.001 concentration, minus 1 log K means 0.1 concentration, 0 log means concentration of 1 m. So at concentration of 1 m, you can see all of them are coming to one place. This represents that at higher concentration, K absorb is very, very low. You can see it's almost low, or there is no binding, right? So at higher concentration, the K absorb value is very low. That represents that the binding of the ligand to the nucleic acid depends upon the salt concentration. So higher salt concentration, the binding of the ligand is not favorable. It shows a lower binding constant values. So the salt dependence K absorb for this is the K absorb for binding of polyuracil, that is a different polyuracil molecule to a series of oligopeptides. Means different peptides varying with positive charges. Means like let's say 2 amino acids having 2 positive charge, that is dipeptide. If 3 amino acid, that is go to tripeptide. So like that oligopeptides, right? So with the different charges. So each oligopeptide log K absorb decreases linearly with log K plus log M plus value. That is, as the log M value increases, that is the concentration of salt increases, the K absorb value also decreases, and the slope, the Z psi, what we call the coefficient or the constant, is proportional to this log oligopeptide charge, and psi is almost equal to 0.7 for single stranded nucleic acid, and Z psi is generally large. The decrease of K absorb with increasing salt concentration is also quite large. So in case of a duplex nucleic, that is double stranded DNA, the psi is conservative around 0.9 due to the charge density of double stranded nucleic acids. Right, so here we can clearly see from this graph that the K absorb totally depends upon the concentration of salt. So the release of thermodynamically bond counterion into bulk salt provides a favorable entropic contribution. That we say, right? The release of cation from the surface of the nucleic acid, which is bound electrostatically, the sodium ion or the potassium ion from the salt, which is bound to nucleic acid, when it is released, so there is a thermodynamic contribution, a favorable entropic contribution, a positive delta S is contributed to the free energy of binding. So that is a free energy of dilution. So this free energy of dilution has been referred to as a polyelectrolytic effect. That is an effect, an increased entropic effect caused due to the release of cation from the polyanionic surface, increasing the free energy. So this is called as an polyelectrolytic effect. And for a ligand nucleic acid equilibrium occurring in a monovalent solution, it is given by the known equation delta G is equal to minus RT ln K absorb, and the log forms of this when we have this coefficient. So the delta G value for a particular electrostatic interaction we can see it as is equal to Z psi RT ln M plus, and because log KB if you take, that is Z psi, so log KB ln KB is substituted to Z psi ln M here, right? So if you take this way here, so log ln KB absorb will go to minus Z psi ln M plus. So that is what is substituted in this equation, right? So this equation indicates that the polyelectrolytic effect, right, that is the delta G due to the polyelectrolytic effect, is eliminated at 1 m concentration, which is the standard state for the reaction. This effect provides a driving force for the interaction of simple oligocations with linear nucleic acid at low salt concentrations, right? So as we all seen in the graph that at higher concentration, 1 m concentration, the binding is very low. At low concentrations only the binding is high. So that is due to this polyelectrolytic effect kind of thing. So how the cations, like if it is a monovalent cation and divalent cation, how they affect this K absorb value, the competitive effect of this monovalent and divalent cations kind of, that is also has been studied. So the K absorb value, the effect on K absorb value caused by divalent cation such as magnesium 2 plus are correlated similar to that of a monovalent. So same, the kind of interaction is more for a divalent. So monovalent will interact with one phosphate, but divalent can interact with two phosphate groups and balance the or neutral the charge kind of thing. So however the coefficient, that is psi, in the energy equation is replaced by phi with respect to a divalent cation. So for monovalent cation, psi is used as the coefficient, but in this case we use phi. So phi represents the number of divalent counter ions that are thermodynamically associated per phosphate group in the nucleic acid. That is one divalent cation interacting with how many or nucleic phosphate groups, or one per phosphate group how many divalent cations are existing. That is given as phi. That is one phosphate group can just needs only half of a charge neutralization from the divalent cation. So the psi values are always lesser than the psi values. So you can see the for double stranded DNA, bDNA form, the phi value is around 0.47 only, and for single stranded polyuracil it is only 0.425. And the ratio, that is the K absorb versus salt concentration, if you take the constant is given as xi psi, that is replaced by phi by psi, which represents for a double stranded the phi by psi ratio is around 0.53, and for single stranded it is around 0.6. So this equation does not hold good for a particular ligand nucleic acid interaction. Then this suggests that the salt effects other than those due to counter-ion release from the nucleic acid should be considered. That is, if this equation is not holding good for a particular nucleic acid interaction with a ligand, that means the salt is not affecting, the salt concentration is not affecting the interactions of the ligand with the DNA. But there is some other kind of, apart from electrostatic interaction, there is some kind of interaction which is causing the binding of the ligand to DNA. So the kind of interaction of the ligand to DNA can also be understood from this relation kind of thing, right? So so we have seen that the divalent cation has got more stronger interaction than the monovalent cation, and it will affect the binding of ligand to the nucleic acid. So let's see in a how the equation, thermodynamic equation, the equilibrium changes with respect to this. So in a buffer containing both monovalent as well as a divalent cation, if we take the dependence of K absorbs, that is the binding constant will depend upon M plus ion concentration, but it is complicated due to the competition. There is always a competition between the +2 ion and the +1 ion to bind to this nucleic acid. So this binding, cation binding to nucleic acid, so this follows a particular equation where we have already talked about, D plus Lz, L to power Z plus, that is the charge of the oligocation, the molecule which is binding to DNA, and how many divalent ions is released from the nucleic acid and how many monovalent ions is released from the nucleic acid. So in absence of preferential ion interaction, the result of M monopositive by dipositive cation competition will be twofold. But that is the value of K absorb as well as log K absorb by log M will be lower than the values in absence of divalent cations. That is log K absorb by log M will no longer be dependent on M plus concentration. So that is has a salt concentration has the divalent cations is existing, the K absorb value will not depend upon the monovalent salt concentration, but it will depend upon the interaction of the divalent cation with the nucleic acid kind of thing, right? So the plot of log K absorb as log M will display curvature. It will not show a straight line, but it show a curvature in presence of M2 plus ion. So this effect results from the fact that log K absorbed by log K measures only the release of M plus. So here this particular graph talks about only the concentration of monovalent ion, but doesn't talks about the dependence of K absorb on the divalent cation, because the isotherm is measured with respect to the monovalent cation kind of thing, right? So, but in presence of a divalent cation, this salt dependence of the K absorb is not seen. So it shows a curvature kind of thing, right? So when both M plus and M2 plus ions are bound to nucleic acid, less M plus will be released on formation of ligand nucleic acid complex, and the binding of M2 plus itself will be function of M plus. Since it also is positively charged ligand, therefore the coefficient of X and Y in the equilibrium equation will change, with M plus resulting in a non-linear plot for log K absorb versus log M. Right? So in presence of M2 plus, because M2 plus will more strongly bind and number of M plus ion binding to the nucleic acid will be less. So divalent ion binding more strongly to nucleic acid, and monovalent ion, number of monovalent ion bound to nucleic acid is less. So when the ligand binds to the DNA, the M plus ion, the monovalent cation that is released from the DNA is less. So the K absorb value dependence on to the salt concentration is not seen, because the amount of monovalent cation released is less. So because the X value, if you see, if I take when the ligand is binding to the DNA, the number of X that is monovalent ion coming out will be very less. So that will not affect the K absorb value. It is not contributing to the free energy of entropy, because more number of M plus ion is bound to the DNA, which is released very less kind of thing. So this interaction is more effectively explained by a theory called as polyelectrolytic effect given by Reocords. So Reocords polyelectrolyte theory. So Reocords polyelectrolyte theory has given this particular equation which tells about the coefficient of binding, that is minus Z psi. This was given by Reocords and co-worker, and they have studied about different molecules, cationic molecules like dinomycin, ethinidium bromide, and ruthenium complex, delta and lambda isomers of ruthenium, and their interactions with the DNA, double-stranded DNA, it has been shown. So for what they said is for a positively charged antibiotic molecule, the dependence of its ionic strength arises from the coupling of a drug, or that is the ligand, and cation binding to DNA. So you can we can see that this is in terms of sodium ion concentration versus log K absorb. So you can see for ethidium bromide and dinomycin, which is having +1 charge, right? So they are having a slope of around minus 8.4 and minus 8.0. That is minus Z psi value is around 0.84 and 0.8 for dinomycin and ethidium. Okay. So ruthenium complexes, they are having +2 charge. So their Z psi values experimentally it should be double of this, that is 1.6 or 1.7 range, but they show slightly lesser value of 1.3 and 1.24. The slope is greater than these monovalent ions, but the slope is not as expected as from the theoretic value kind of thing, right? So the plot clearly shows that the salt dependence of delta and lambda RU complex binding to DNA, and also for dinomycin and ethidium, that are known to bind by intercalation. So the dependence of binding constant of these compounds on sodium concentration is a consequence of linkage of ligand and nucleic acid, right? So the lower slope value for the ruthenium complex is due to the interaction of the sodium ion to the nucleic acid kind of thing. And it is analyzed by the polyelectrolytic theory. So based on polyelectrolytic theory, the data indicates that ethidium and dinomycin both having +1 charge has a slope of 0.8. Right? This we have already said that in case of ruthenium complex, it is having a plus charge of +2, and it shows a slope of 1.37 and 1.24 respectively. So this minus Z psi value for ruthenium complex is lesser than the expected values. So these lower values arises from the coupled anion release or from changes in ligand or DNA interactions upon binding. So the kind of binding to the ligand to the DNA also affects this kind of nature, right? So polyelectrolyte theory have been used to describe the thermodynamic linkage between the cation and the charged ligand binding to the DNA lattice. The cations are condensed. So what is Reocords theory? What it says is that the cations in the salt are condensed around the DNA, that is the nucleic acid. It condenses around the nucleic acid negative charge and creates a positive cloud around it in order to neutralize the negative charge of the nucleic acid candle. And these cations are non-specifically bound. That means they are mobile. They are not specifically bound. That is one cation binding to only one phosphate group. It's not. It is binding. It is existing, condensing around a region where it is neutralizing the negative charge of the whole nucleic acid kind of thing, right? Wherever the negative charge existence is there, it gets condensed. So these cations, they are not static, they are mobile. They move in a particular region. So they are non-specifically bound. So binding of a positively charged ligand to DNA results in release of these bond cations, and because these are also positive charge, because of the positive charge on the ligand, and it neutralizes the DNA negative charge, right? So the cation and the ligand binding are thus thermodynamically linked, and the binding of one influences the binding of others. So binding of a positively charged ligand to the DNA influences the binding of this cation to the DNA. So the dependency, how it is being given is based upon this particular equation, the thermodynamic equation, that is logarithm, natural logarithm of K absorb is given as natural log of the K naught T, where K naught T is called as a thermodynamic binding constant and K absorb is called as the apparent binding constant, where the gamma is represented as the mean activity coefficient of the monovalent ion, and particular constants have been included, that is 4.2, and delta, that is plus or minus value for it, for the Z values, and the concentration kind of. So the magnitude of, see here there is one plus missing, please add that plus here, right? The magnitude of K naught T indicates the extent to which non-electrostatic forces stabilizes the ligand DNA complex. Larger KT indicates binding through intercalation, that is how the nucleic acid binds to the ligand. If there is intercalation mode, the number of cations released might not be same as that of the normal electrostatic interaction. So larger KT values indicate there is an intercalative mode. So thermodynamic equilibrium constants may quantitatively assessed once Z psi is known, and corrected to free energy for coupled ion release, and referred to standard stage in which concentration of salt is unity. So this thermodynamic constant helps in determining the possible mode of binding also, that is if it is an intercalative mode kind of thing, and K absorb is called as the apparent bind. So the total binding constant what we get is it involves a thermodynamic concept as well as the charge of the metal ion as well as the charge of the cation that is involved in the binding to the nucleic acid. So this is a comparative energy levels of energies for ligands, like say ethidium, its K absorb values around 49.4, delta G around 0.77, slope was 0.8. The thermodynamic constant here it shows on 6.1. But in case of say delta ruthenium complex, K absorb is very low, 0.97. Delta G value is slightly higher, but you can see the K naught thermodynamic value, if you see it is 0.02 only. So there is a large deviation for ethidium bromide and dianomycin K naught T values to the ruthenium complex. So this indicates that the ruthenium complexes are not intercalative in nature, their binding is slightly different. So ethidium and dianomycin has large KT values, whereas delta ruthenium and lambda ruthenium complex have very low K naught T values when compared to their K absorb. K absorb are also very low. So this indicates the ethidium dianomycin binding to through non-electrostatic binding. right? Whereas the binding of ruthenium and lambda complex, lambda ruthenium and delta ruthenium is predominantly by electrostatic nature only, because the cationic effect is more influenced there, so the K absorb value is also less, as well as the K0 T value is also less. So they are binding through an electrostatic interaction rather than intercalative mode, but ethidium bromide and dynamycin bind through intercalative mode. So this K absorb values can be helpful for determining the mode of binding also based upon this thermodynamic equation. So the K absorb which is obtained from this delta G absorb values. So delta G absorb values can be split into a non-electrostatic interaction and a electrostatic interaction free energy. So the electrostatic interaction free energy is from the Reocords polyelectrolyte theory, which is about minus Z psi RT ln m plus. Right? So if this value is high, that means the interaction is electrostatic in nature. If this value is low, that means the interaction is non-electrostatic in nature. So that we can see from this like doxorubicin, which is an intercalative, which shows a non-electrostatic interaction of minus 7.8 and electrostatic interaction of only minus 0.1. And hydroxydubicin, if you see, the electrostatic interaction is very low, minus 0.2 only. So this represents that here it shows a very low electrostatic interaction. That means the here non-electrostatic interaction is more, kind of thing, right? So these values are helpful in determining the interactions of ligand to the nucleic acid and kind of interactions, electrostatic or it is a non-intercalative interactions kind of thing.